Okay, so I've posted the answers to that on Moodle, so you need to look again. The equilibrium constant K. If you understand what a quotient is, this makes perfectly simple sense. If the K is high, then the products must be favored. Look, if this number is high or large, then that must mean that fraction is large, and that part of the fraction is small, because a big number over a little number is a big number. Okay, so the big number comes from the top, which are the products. So if I have a lot of products and a little reactant, that means that this arrow here means I have a lot being made into products and just a little bit decomposing, in this case, into the reactants. So to put percentages on this, this is like saying I've got 98% doing that thing and 2% doing that thing. I'm making these percentages up, by the way. But do you understand what I mean? So we say the products are favored. So what's a big number? Well, here's a big number. 1.7 times 10 to the power of 2. So that's 170. Yes, everybody? Yeah. Okay, you have to be okay with these scientific notation. 170 is a large number for a K value. Okay, so this means that this must be high, which means that this concentration must be high, and these concentrations must be low, meaning when I try to burn coal, that's what this is, right? Yeah. If I'm burning coal, I get a whole lot of carbon monoxide made. And very little of that carbon monoxide decomposes back into carbon and oxygen. Doesn't that make sense to you? How easy do you think it is to take carbon monoxide and go back into carbon and oxygen? Not very, right? You got that in your head? That this is going to be a very small concentration, that's going to be a very large concentration. Okay. So, and likewise, if it's low, then the reactants must be favored. So here is a solubility, really, issue. So if I have a low K value, like 1.7 times 10 to the power of negative 7, or negative 10, I mean, is very, very low, very small. It means that these concentrations are very small. So that means that the products were very small and the reactant is very large. That means I get a lot of solid and a tiny bit of ions, which means that this is highly insoluble. Okay? So this is not a very soluble ionic compound because the K value is very small. Sometimes, whether the products or reactants are favored is expressed as a percentage. So here you go, like that. And I've been doing that already a little bit. Okay, so this relates to percent yield. So how much of your products at equilibrium divided by the maximum amount of products we could make if it was all 100% dissolved or reacted or whatever. So this is sometimes called percent yield and sometimes it's called percent reaction. So let's take this. We're going to have nitrogen and hydrogen and we're going to put them together to make ammonia. We've talked about this. This is the precursor to then go and make a lot of fertilizers. Remember that? Fertilizers. So this is an important industry where we take nitrogen from the air and hydrogen. This hydrogen can come from water, but mostly it comes from methane, the decomposition of methane, and put them together to make your ammonia gas, which is then used to make fertilizers and bleach and etc. Okay. And we're going to talk about that equilibrium a lot this unit. If I take 0.1 moles of nitrogen and we produce 0.15 moles of ammonia, okay, that's the fact. But if you're doing this stoichiometry-wise in Chem 20, you would have said that if I'm taking 0.1 moles of nitrogen and it's a 1:2 ratio, I should get 0.2 moles of ammonia formed. Everybody agree with that? That stoichiometry-wise, go down the column, that's the number of moles there. Go across the bridge using your 1:2 ratio. If for every one of these I make 2 of these, then 0.1 should make 0.2. I don't make 0.2 though. In my factory, I only get 0.15. Why is that? Because of this equilibrium. Because it's not 100% lovely little conversion, but rather it's equilibrium arrows. So percent yield says, this is what I get in my factory. This is what I could have got if I did it 100% yield-wise. So I'm only getting 75% of my yield. Everybody okay with that? Okay. And another little tidbit of information is Nick went and wrote down his equilibrium expression upside down. Right? He wrote, instead of products and reactants, he accidentally wrote reactants over products. Right. So actually what he found wasn't KEQ, but he found the reverse. K reverse, if we were talking about it from the other perspective, the decomposition of it. So the K reverse is equal to 1 over the K of the forward. They are reciprocals of each other because it's products over reactants, so reactants over products. They are reciprocals, so these are reciprocals. So if this, which decomposes in, this is an acid, carboxylic acid, it's a weak acid, therefore I have these fancy weak arrows. So some of it, a tiny bit of it, decomposes into H+, that's why it's an acid, and this ethanoate ion. The K expression for this is 1.8 times 10 to the power of negative 5. That's quite small, which tells you that these are small in concentration, and this is large in concentration, which tells you that the equilibrium favors the molecular compound and not the ions, because this is small. Right? Small is small number over big number. Okay, so if I asked you, right, what is the K value for the reverse, for the ions becoming an ionic compound, all you have to do is take that and go 1 divided by that, and you get your K of this reaction now. Okay, so in this solution, most is molecular. In vinegar, in ethanoic acid, most of it stays, and very little of it goes this way, and that's why it's such a weak acid, because you only get a tiny bit of concentration of H+. And that's a whole big chapter in this unit. It's talking about weak acids. Yes?
Okay, so the K for like the top one here, like that's just like the regular one, right? Like that's what we've been doing.
Yeah.
So then for this one,
yeah.
So if you just ask for the reverse, we'd find that and then just do 1 over. It's just the
Correct.
easiest to carry.
Correct.
You can't just do like reactants over products.
Well, you could if they gave you the numbers for it.
Okay.
But what if they don't give you the concentrations, they just give you this? Then you have to go 1 divided by that.
Okay.
Okay? Okay, so here are some questions that are going to put all of that together. I've only circled 2 and 4 because those are the ones we're going to do for now. Actually, let's circle 3 as well. We can do all of these. Why have I circled 2 and 4? Yeah, you can do... Yeah, you can do all of them. Okay, let's do all these questions. And I think that'll take us probably to the end of class. And we'll do this tomorrow.